That's what I'm supposed to see?
Yeah, I think that's what you're able to see. So I will introduce you.
Should I share a screen?
And then, yeah, you can share a screen.
No, sorry.
Perfect.
No, I didn't share. Maybe. Okay, I think this is.
All right, great. Welcome back, everybody. We're going to start the next session. We're going to be hearing from Itai Ashlagi from Stanford, and then Bo Waggoner from UC Boulder. This session, we're going to be looking at more at going back to contracts, contract design, and applications, and then connection to scoring rules. So first up, we have Itai Ashlagi, Stanford, who will be joining us remotely today, and he'll be talking about simple and approximately optimal contracts for ecosystem payments. Itai, go ahead. You have 35 minutes.
Thank you. Can you hear me? Okay. Okay, so this is joint work with my student Itai, who actually graduated now. And now she's actually, she was interested in her PhD in sustainability, and actually now she's in Chainlink. And Irene Loh, who is my colleague at Stanford. And I want to thank the organizers, Brendan and Michal, for inviting me. This work is really the fruit of Wani's interest during her PhD, and I'm really just delivering it. So what we are interested here is using contracts to understand the impact of payment for ecosystem services. So it's a widespread phenomenon now, and actually there's about $40 billion a year used by NGOs and governments to pay landowners or natural assets owners for ecosystem services for things like watershed, to reduce deforestation, to conserve their land, in order to maintain in order to maintain the land and for the environmental benefit. Now this is a widespread phenomenon across the world, including developing countries and developed countries. And a lot of the programs are through the United Nations, for example, the Red Plus. There's a widespread, for example, in Costa Rica, in Ecuador, and so forth. But one example for a specific program that I would like to mention is in Uganda, where there was a randomized control trial for a payment for ecosystem services, which was done by development economists and together with some NGOs, by Seema Jayachandran. She was in Northwestern, and what they found is that payments actually help and reducing up to 50% of deforestation. At the same time, there's a lot of mixed empirical findings, and it doesn't always help. And we see a mix between up to 50% to no impact at all of such payment systems. And this is where we wanted to come in to get a little bit more of theoretical understanding when those PS systems can work. And we're going to use the language of contract design to understand this. So let me just organize here something. Okay, so you can write down a model where there's a principal and an agent, where the agent is the farm or the forest or the landowner, and figure out what is the optimal contract. What we're really interested in here is figuring out what is, how do simple contracts work. So if you look at the PS programs around the world, they're very simple in how they're implemented. And the most widely used type of contract is a conditional contract, which is essentially saying, I'm going to pay you only if you conserve the entire forest, and otherwise I don't pay you anything. And a simple question to ask is, when are those conditional contracts actually effective? And when they're not effective, are there other simple contracts that actually can be better designed and achieve some benefit? Okay, so what I'm gonna do in this talk is set up a simple principal agent model, actually borrow a lot of the ingredients from some already existing papers from two development economists. And we're gonna ask, we're gonna see what is, I won't describe exactly, but there's gonna be some properties of the optimal contract which we are not so excited about, but we're really interested is what are the performance of simple contracts that can actually be implemented in practice. And the last part will be a quick numerical exercise using on some calibrated data to see the insights from the results themselves. In terms of literature, there's a lot of literature on PES, but not just some of this in economics, some environment, some surveys. What we're really building here is a paper on the theoretical approach by Mason and Platinga. We're gonna use ideas from contract design, of course, but also use ideas from robust contracts where we want to make the contract simple. We're gonna try to use things like distribution free. And there's some interesting surveys out there. Here's one of them by Alex Teitelbaum, which is a very nice survey for natural capital market design that I recommend to read. Okay, so let's jump into the model. And again, this is based on Mason and Platinga. So the key thing that is observable is going to be the land that the agent owns. So this is going to be A naught. And you can think about this as I can see, for example, how much forest there is on the land because I can maybe see through the satellite. So this is publicly observed by the principal. And the principal here you can think about as the NGO or the government, and the agent is the landowner. What is not observed to the principal or to us is the private baseline conservation of the agent, which is going to denote by theta. This is going to be some number between 0 and 1. You can think about this as the percentage of that he's conserving from his own land. And it follows some distribution f theta, which I'm going to assume that is known to the principal. So the agent can, with this type theta, can choose to conserve any amount of land between 0 to his own amount of land. So this is going to be some upper bound. And it's going to do so with some conservation cost, or you can think about this as the opportunity cost to conserve this amount of land. So any amount that is going to conserve here, any amount that is going to conserve here up to theta is going to be essentially cost 0. This is what he's going to be conserving if there was no contract at all, what he's going to do anyway. And after theta, it's going to be a convex cost. So you can think about this, for example, as once there is a contract there, the first piece of land that is going to conserve is the one that is the least valuable for agriculture use. And after that, it may be more and more costly to conserve this land. Okay, so, and now there's some coefficient here, H. You can think about this, that's relative value for land for the agent. The agent utility is the payment minus that he gets from the principal minus his conservation cost, or minus his opportunity cost. The principal going to have some environmental value for the land, and so we're going to model this as K dollars per unit area. And now we're going to make here a linear assumption. It's going to be, so there's a linear assumption here on this environmental value. And one way to think about this is this captures for example, the carbon removal from the atmosphere. But it doesn't capture things like biodiversity or complementarities between if you want the agent to conserve contiguous parts of the land or things like that, that I think this is very interesting for future research. Or if there's multiple agents that we don't model here, and you want them all together to have a continuous part of the forest conserved. So this is a non-trivial assumption, but it doesn't capture a lot of things that are interesting, I think, for future research. The principal selects a contract that is essentially paying the agent some amount to conserve for land that is conserving, and is trying to maximize this objective. So this is the K, the environmental value, times the expected amount that is going to conserve minus the expected payment. And this is standard constraints to make to take into account the strategic behavior of the agent. So we are imposing here incentive compatibility, individual rationality, and limited liability. Limited liability just means that we're not charging the agent anything. We can only pay the agent. So this is, to solve this problem is standard exercise in contract theory. And you can derive the optimal contract. You can use this idea of direct revelation contract, where you're essentially picking a payment and how much the agent is going to conserve. There is a boundary condition here because of the amount of land that you can conserve. And if you solve this, if you write this down into mathematical notation, you're essentially picking how much the agent is going to conserve, what is the payment. Incentive compatibility just means that the agent is better off reporting their own type over some other type, theta prime. In terms of the utility, individual rationality just means that they are happy to participate in this contract, and limited liabilities that we never charge. Okay, so you can solve this using standard techniques. So there's nothing novel here. And what you get is, here's an example for an optimal contract when the distribution for conservation follows a uniform distribution between 0 and 1. And what you see here is the direct optimal contract. On the left, you see the payment structure, how it depends on theta, and on the right, how it depends on theta, the conservation quantity in the optimal contract. What is a little bit complicated here is that it highly depends on theta, of course. And essentially, if you think about an agent is going to, that has to decide if to participate in this contract or how to behave in this contract, then it's essentially seeing infinite amount of menus. So you see the slope here, for example, is not linear, and he's seeing infinite menus. And what we want in this paper to understand is how do simple contracts behave. And just begin with, for example, is this conditional contract. Okay. Another problem with this contract is highly dependent on the distribution F. Okay, so we're going to try to understand what the performance of simple contracts. Specifically, again, the first thing is we're going to look at is conditional contracts, which are paying the agent if and only if he conserves the entire land. So there's no deforestation at all. The next set of contracts that we don't see almost in practice are linear contracts. And by linear contract, I just mean there's a payment per amount of land that you're conserving. There's no conditionality here, but the payment is not depending on your type. And in the paper, we also extend the analysis to conditional linear contracts where you pay per amount of land, but only if the amount of conservation is exceeding some threshold. And the way we're going to measure performance of these contracts is by taking the ratio between the expected value for the principal in the simple contract divided by what the principal is getting in the optimal contract. Okay. Okay, so let's start with conditional contracts. So again, this is only paying if you conserve the entire land. And you can write this down in a mathematical way and analyze this. And what we find is a very simple characterization. There's three regimes, basically, that are characterized by this quantity K over H. K, again, is the environment value for the principal. H is essentially, you can think about the land value for the agent. And so this ratio between them is the key quantity. So when it's large, you essentially get, by using the optimal conditional contract, that it achieves the maximum or the optimal contract. Okay, so they both achieve, the best conditional contract achieve what we call the second best. When K over H is small, there's no reason to use a contract at all. And again, the best conditional contract, which essentially just let the agent do whatever they want, and they're going to use the baseline conservation, is going to be optimal. And where it really matters is where it's in some intermediate regime. And in this case, the best conditional contract can be performing arbitrarily poorly. This ratio between them that we showed can go to zero. Here's a simple example to illustrate this. This is an example with a degenerate distribution. You don't need this. You can have a slightly different distribution. There's one agent type. And so there's essentially no information asymmetry here. And the conservation and the land is, let's say, normalized to 1. The best conditional contract is either to not offer anything to the agent, or it achieves K minus H over 2, which is essentially paying him to conserve exactly everything, and that's what you get. Okay, and you will do the left side if it's larger or equal than 0. And it's not a surprise to show that if the optimal contract always achieves something that is positive. So in this case, if the optimal conditional contract is not to do anything, you're going to do arbitrarily. So this brings us to look at the different class of contracts. We're going to call them the linear contracts. And there could be other types of contract that are maybe distribution free. Here, we're looking at this specific one. And we're going to pay an amount that is proportional to the conserved forest area. And what we're finding here is identify the contract, essentially the payment per amount of land that you're conserving is going to be K over 2, and that achieves half of the optimal contract. Okay, in terms of value for the principal. Okay, this means in particular that the best linear contract also achieves at least this half. The idea for the proof, I won't write down the proof here, but what we do is essentially write down what is the value for in the optimal contract, what is the value for the principal just from the environment minus their payment, and we we drop the information rent because of the information asymmetry, and we show that the best linear contract, or the linear contract that we identify here, is achieving half of this upper bound, and therefore it achieves this, it derives this theorem. So this theorem says that it doesn't matter what f is, what h or k is, we achieve the half of the optimal contract. This is in particular distribution free because we're just picking a payment that is k over 2. It does depend here on the slope of the cost function. So remember, the cost function that I've assumed is quadratic, and the ratio of here will change if this cost function will change. It will depend on the curvature, and that we extend this in the paper to see how it depends on the curvature. So if you summarize those results together, when the relative environmental value k over h is low, you don't want to use a contract at all. Just let the agent to behave as if there's no contract. If it's high, the conditional contract is optimal, and the linear contract is actually suboptimal. Where the linear contract kicks in is where in these intermediate regions. And that's where what's intermediate and not is an empirical exercise to understand. So we're not saying that necessarily a linear contract is the best, but there are regimes that we should be aware that it might perform better than a conditional contract. Okay, so this brings me to, so we have here, this is the table summary. What we're doing next in the paper is do a simple numerical study where we don't have data for these parameters in developed countries, but this paper, Mason and Platinga, what they do is they calibrate data from US land. So they take 140 regions in the US, and they do some estimation for the based on conservation distribution and the conservation cost. So the cost is something that is maybe harder to observe, but we are using this as an exercise. And specifically, what I'm going to show you is, for example, Montana. And here's one of the what they also do in the paper before this is that they do these calibrations, and they also split the regions into regions with low risk and high risk for deforestation. The risk comes for example, if the land is very good for agriculture or not. So here's, for example, this a low risk area in Montana. In this case, corresponds to the expected theta is large. And on the x-axis, you see here the environmental value. And on the y-axis, you see the percentage of the optimal contract. So this is all normalized to the optimal contract. And what you see is that on the left is, so maybe before this, the graphs correspond, the blue is the conditional contract, the red is the linear, baseline is the green. And whereas the gray area is where the linear outperforms the conditional contract. So you see here on the left, the Alcon side, when the environmental value is higher, the conditional contract becomes better. But here there's a small region that the linear is better. Now, it doesn't look like a lot better, and the region where it's better is not large. This is exactly when there's low risk for deforestation. It's more interesting if you look at the high risk deforestation risk, then the gray area where linear is better than the conditional is much larger, and also the gap between them is much larger. So we really want to understand better empirically where there's high deforestation risk, and what is K and what is H, and so forth in practice, in order to make use of those kind of results. You can take, if you're an NGO, you can take some specific environmental land. For example, K equals 100 corresponds, according to their estimates, to $50 per ton of carbon. what you can all, and then compare the two between, see if you're in the high risk or the low risk, if it's bad, what kind of contract is valuable. We don't have, as I mentioned, any data for estimates for developing countries, but you can do some kind of back of the envelope calculation. So if, for example, if the conservation cost in Brazil is going to be half than in the US, that corresponds roughly to scaling the environmental value by twice, and maybe then instead of 100, it moves to 200. Okay, this is just a hand-wavy way to think about this. But we really don't do anything empirically. Okay, so to summarize, what we're doing here essentially is taking the language of contract design to develop payment, to understand how payment for ecosystem services can perform. And it's really just a first step, I think, to think about issues in climate change. And I think there's a lot of potential here to do mechanism design and contract design in this area. In this paper, we've seen that conditional contracts can perform arbitrarily poorly. Conditionality, this restriction is just too harsh, and what it does is just low take-up. Very few agents will actually be interested in such a contract. And a linear contract can guarantee half of the optimal payoff. And it's better than conditional in some regime, especially those intermediate regimes of K over H. We did a numerical study with the US land data and to describe how to get a sense if the results are interesting or not. Some extensions I actually want to highlight. First of all, in the paper, what we do is also look at the conditional linear contract that, not surprisingly, are outperforming the linear contracts. Sometimes they coincide with them, but they're getting best of both worlds. We show how this performance ratio depends on the cost functions. More importantly, I think, is opportunities for future research. And I think one of them is this complementarity in the forests. So suppose you don't want to you want some contiguity in the forest. Another thing is if have multiple agents who are living next to each other and or the lands are next to each other, what do you do in those scenarios? Maybe there's room to think about contracts for, use the ideas of contracts for teams, or even a mechanism design approaches. Other things that are important and comes up in many of those surveys are stochastic shocks or costs for the agents. You want to have steady income and over the years. So if you think about long-term contracts and not just a one-shot like we did here, you want to think about modeling how to guarantee some income over the long run. So I think there's a lot of opportunity here in these few future directions that I mentioned, and probably yeah. And I will end here, and if there's any questions, I'm happy to use the time for questions.
Great, thank you very much.
Questions?
So in your model, there is a baseline conservation. So the agent has a cost, which is the square distance between the outcome and the baseline. So I wonder, do you have an explanation for why, if there is a worse outcome, the agent still have to pay the cost?
The agent is okay. So the agent is essentially paying this opportunity cost. So I'm offering him a payment, and for conserving some amount of land, and if he can take it or not take it, but and then he decides how much to conserve. Right, and he gets paid. I'm not charging him anything. The cost is essentially his opportunity cost for conserving this amount of land.
Okay,
Does that
thanks.
make-
Yeah. And I have another question is, there's a paper, Carroll 2015, which is in American Economics Review, which is, has a title, Robustness and Linear Contract. In their paper, they show that linear contract is optimal, or maximally optimal, and it is robust. So I wonder, can you talk more about the difference between, if you know about that paper, is there a difference between your result and their paper?
Yeah, so in Carroll's paper, it assumes that essentially there's some actions that the principal is not aware of. Here, all the actions we are aware of. These are actions between 0 and conserving their amount of land. This is not unobservable. In his case, that's the max min is over that set of possible actions that he's not aware of. Here things are known. What we are doing here when we are looking at the linear contract, we're picking some payment that is going to do well. We know the distribution. The best linear contract may depend on the distribution. What we are identifying is one that is distribution free. But we're not assuming to begin with that we don't necessarily don't know it. So all the action space is known, the distribution is known. We happen to find also a one that is distribution free that performs well. It's not, but it's against the one that is in expectation does well. In his case, it's max min over the set of actions that are not known necessarily.
Okay, that's clear. Thank you.
Other questions? Great.
There's another paper by Duting et al. In Baltalgam and Duting in Baltalgam and Tim Roughgarden, who do something in the spirit of Carroll, but they also there's a distribution, but all they know is the first moment of the distribution, and then they do a max min over the condition on that first moment. So again, it's different in the sense that we know the distribution. So in this paper, everything is classic contract theory, but we just do a more applied kind of approach to avoid maybe using very sophisticated contracts that NGOs may not want to use in practice. And it's interesting to actually think about taking their approaches into this area as well.
So it seems to me that your setting here is kind of like the best setting to question limited liability, because you say that if someone does not do the minimum conservation, then you could charge them something. And I was wondering whether you have any thoughts on that. And I actually don't know if there's any literature on that in contract design.
Yeah, that's an interesting thought. We didn't think about that. We were taking the approach of here's this NGO that doesn't want to charge the agents. The governments definitely could maybe do something like that. I think that's a great question. I didn't think about this much. It's a good observation.
Was there another question?
And in terms of literature, I haven't seen, definitely not in the PES literature that we surveyed, anything like that.
Oh, okay. But do you want to? Okay.
Yeah, so thanks, Itai, for the very nice talk. So I think you already partially answered my question, but I think like with the distribution and assuming a first moment that like linear contracts are max min optimal, but I think maybe there's like a a different question that one could ask here, right? Because I understand like your approximation is not even using the moment, right? So it's just dependent on this k/2. So there could be a question of what's kind of the best distribution-free contract. Do you have some sense of like how close to being optimal in that sense linear contracts are?
Yes, I'm not so sure. Even the k/2 does depend on our cost function. So that it won't be k/2, this payment, or the ratio is not going to be half if the cost function is different. And so I'm not sure what's going to be, but even under the quadratic cost, what is the optimal distribution fee? I'm not sure. My guess is that it's not going to be either half or close to half, but that's a very wild guess.
Great, thank you. I have a question actually. So you had mentioned an extension to stochastic costs, you know, like shocks and so on. I guess another extension one could think of along similar lines is to have heterogeneity not just in theta but in H. You know, like different people have different like land quality or something like that makes conservation harder. And I guess I'm curious whether the distribution freeness and robustness of these contracts sort of like if there's hope to say that these results sort of extend to situations where there's heterogeneity on that side as well. Or is this something
for heterogeneity in H, it works because this contract is fine in the linear contract gives the approximation for any H as well. Stochastic shocks well, that we need to model. I'm not sure exactly how this falls into this question, but the way I think about stochastic shocks is suddenly there's a bad year in terms of what agriculture or things like that. So it's really more futuristic. But heterogeneity, for example, in H, that captures that. What other things were you had in mind?
Well, I guess I'm just wondering, you could imagine that you have some farmers that are in the regime where conditional contracts work well, and other farmers that are in the regime where linear contracts work well. Is there hope that there's a like linear contract with a conditional linear contract that sort of does well across the whole range?
Yeah, I see. Yeah, so that I'm not sure. So it does guarantee you half for everyone, but if maybe half is really bad if you have a lot of agents in the high regime and a lot of agents in the low regime, then it's maybe not so great. That's a good question. I don't know the answer more than to do anything better than that.
All right. Well, thank you very much. Yeah. Let's thank Itai again. All right. So next up, we have Waggoner. We just want to get set up.
Oh, sorry. Do this, right? Full screen.
Control L, I think.
Nice. Oh, awesome.
Okay, great. So Bo will be telling us about contracts with information acquisition via scoring rules.
Great. Thank you. So this is joint work with Manisha Papareddigari. It'll appear in EC this year. And I wanted to start by saying actually we're very grateful to the EC reviewers who pointed out some issues and helped us with relationship to related work. Of course, there's a vast related work in contract theory and in clarity of explaining what we're trying to do. And that's what I want to focus on today. So I want to tell you about this problem of contracts with information acquisition and how we're thinking about this problem via scoring rules, which I understand to be a bit different than how people often think about contracts, so maybe it's interesting. And then hopefully in the EC talk, Manisha will say more about like what is technically interesting, but I might not have time for that as much today. Okay, so we're taking a theory approach to a principal agent type problem that many of us are very familiar with, especially at this point in the workshop. So there's a principal and there's an agent who's going to take an action, So for example, the principal might be like a clothing company, and they're employing a marketing firm, which is an agent. And they're going to run a marketing campaign, and this action they take will influence an outcome of interest to the principal. So for example, sales of the clothing. Okay, and the principal is going to get to observe this outcome. Okay, and then they can choose to pay the agent based on what happened. All right? But the principal, he's sitting up in his office, and he can't observe what's happening, or the details at least of what's happening in this agent's action. So of course the general research problem here is to understand how can we help this poor fellow sort of extract a lot of value from the lazy proletariat down there who's acting. So in particular in this problem, the hidden action has two parts. So first, the agent could choose to gather a piece of information. Okay, so for example, they could try to run a survey to find out what customer preferences are like or something. And then they can choose this action that we talked about, such as which marketing campaign to run. And of course, they might want to choose that action based on what they found out when they were gathering information. Okay. Now, it might be costly to gather information, so the agent might not want to expend the effort to run that survey. They might just want to go ahead with a marketing campaign and hope it works. So our question is about how to incentivize that when the principal doesn't observe any of this stuff. They don't observe anything the agent is doing, only the final outcome, like sales. Okay, so the way that we're thinking about this is taking the moral hazard principal-agent problem, which is this hidden action, and adding this preliminary stage where before taking the action, the agent can gather some information and use that to decide what action to take, but it's costly to gather that information. So that's how we're thinking about what we're doing that is different from previous work. And we're going to think about solving this optimally, so we're not going to think about robustness or anything. Of course, it's not completely new, and people have thought about very related things, but not solving this model that we're going to solve. Although Zermenio has some very closely related things, and these are some other works similar in spirit. Yeah, okay, and they call this a principal-expert problem sometimes, some of these papers. But the stage one is also very similar to the things that Jason and Ifan talked about this morning, incentivizing someone to learn more information. And I'll talk about that. Okay, so first I want to tell you the formal model of the problem, and as I tell you it, I want to tell you how we're thinking about the solution geometrically, and then talk about the results we get, building up in some sense to this main result, but that turns out to be a bit of an anticlimax. It's just saying that there's a polynomial time algorithm for solving this. So really what's happening in between is most interesting. And I'm going to front load the talk even more than that. We're going to actually spend almost all our time in part one. And I just really hope to communicate this model, and maybe we can have some discussion about the model and how we think about it, and then kind of zoom through the rest. Okay. So as promised, we'll take our time. I want to revisit just a standard moral hazard or hidden action problem in the way that we're going as a special case of our model. So I just want to tell you exactly what the hidden action problem is in our setting. So that's going to be the case where the agent doesn't run a survey, for example. They don't gather information. They just decide what action to take or what marketing campaign to run. Then I want to recall the other special case of our setting, which is what we think of as information acquisition. So the agent is going to gather information, like run a marketing survey, and then there's no action for them to take, but we do want them to tell us what they found out. Okay, so you could think of that as the special case of our setting where there's no action at all, but we do want to incentivize them to gather the information. And so I'm going to phrase that model exactly in our setting, and then give our model, which is just squishing these two together. Okay, so this is how we're phrasing the hidden action model, which is a very classical model. The principal is going to start by offering some contract, T, that says for any outcome omega, so for example, for a good sales outcome or a bad sales outcome, here's how much I'm going to pay the agent, the marketing firm. The agent is then going to look at this contract and decide what action they want to take. So for example, do I run a high effort campaign or do I do a low effort campaign? And these have heterogeneous costs. Okay, so the agent may choose one that's less costly or more costly. And then nature is going to draw an outcome from a distribution that depends on the action that the agent took. So if they took action A, it comes from distribution PA. Okay. Then the principal will finally observe this noisy outcome. They'll observe that, and then they'll pay based on that T of omega. Okay, so very, very standard. The main thing I want to mention that's different from the way we often frame contracts is we're not necessarily thinking about the principal's utility here. We don't actually care about it. We're going to solve instead what's called the minimum payment problem. Okay, so that's going to be incentivizing a certain action as cheaply as possible. So here's the setup. The principal comes to us and says, I really want the agent to take this action. And then they ask us, what contract should I offer so that the agent does indeed want to take this action? And how cheaply can I make that happen? Okay. So I want to make sure it's clear that if that's what the principal asks us to do, we don't need to actually reason about the principal's utility. We're not trying to solve that problem. We're just saying, all right, you wanted to incentivize the agent to do this. Here's the cheapest way you can do that. And then as Paul and Inbal point out, if you can solve this minimum payment problem, well, you could solve one of these for every action and use that for the principal to decide how to optimize their utility. Okay, but we're not going to worry about that. We're just going to try to solve this minimum payment problem. And that's assuming the agent maximizes their expected utility. So they're going to look at the contract, and for each action, they'll say, this will be the cost that I have to pay if I do that action, and this will be my expected payment. Expected payment minus cost is my utility, so the agent's going to optimize over that. Okay, and we require limited liability, which is often a standard assumption in these settings. So we assume that the principal can only pay the agent. The agent's not going to pay the principal, and that's related to Hara's question in the previous talk. So we also take this assumption, payments have to be non-negative. Okay, so I mean, this problem and variance are extremely classical. Look at Paul and Inbal's a workshop where they also have a link to their tutorial, and then at some point you'll be able to see like slides and their tutorial from yesterday. So yeah, but I want to show the way we visualize solutions to this problem, because we're going to do the same thing in a more complicated setting later. So let's suppose there are two outcomes that the principal will observe. Either they'll observe good or bad sales. Those are the only two things that could happen, good or bad. And here I plotted the probability that the outcome is good on the horizontal axis. And now let's suppose the agent has two actions. Let's call them H and L. If they take the H action, then nature will draw this outcome from the distribution pH, which has a pretty high chance of a good outcome. If the agent takes the L action, nature will draw the outcome from PL, which is a pretty low chance of good. Okay, what's a contract look like? It's a payment if the good outcome happens, and a payment if the bad outcome happens. So, for example, T of bad, maybe if the principal sees bad, they'll pay 2. If they see good, they'll pay 8. Seems reasonable. And now we think about the expected payment as a function of the sort of distribution on outcomes. That's going to be given by the line that interpolates those 2 points. So for example, if the agent takes the H action, the distribution over outcomes will be pH, and their expected payment over that uncertainty in pH is going to be this T bar. I use T bar to denote expected payment of pH. Okay, so very standard maybe for some of us, but maybe not for all of us, so just want to be on the same page. And so now, given this contract, the agent will say, all right, I'm getting paid more on average if I take the high action, but depending on the costs of the two actions, you know, the agent will optimize and decide which action to take. Okay, so that was just the hidden action model and how we're drawing it. Any questions so far? Yes? Yeah, so the question was, how come when it's 0, I've drawn some payment for the bad outcome? That seems silly. Yeah, so this wouldn't be optimal because, well, actually, you might need to do this if the agent's costs are all quite high. you might have to always pay them, but maybe not at the optimal solution. I forget, actually. But I think that could happen, that you still have to, if you want a participation or individual rationality. So why did I say the outcome is noisy? So what I think of the outcome is a noisy signal of which action the agent took. So if the agent takes action H, you don't get to see whether that happened, but you get something that's a noisy version of PH. Yeah. Thank you. Okay. So now let me tell you about this other special case, and it looks very different, so I want to take the time to frame it in the same way as a principal expert problem. It looks somewhat different, perhaps. And of course, it's very related to Jason's talk this morning, and there's also a paper of Chen and Yu. I'll discuss those a little bit later. Okay, so this is how we think about this problem. The goal, again, is to incentivize the agent to, for example, run a marketing survey and then tell us what they found out. So we first offer a scoring rule. It's a function that takes in a distribution or a prediction over the outcomes, so a point in the simplex, and a realized observed outcome, and it gives a payment based on how good that prediction was. So you could expect that things that predicted the outcome better get higher payment. The agent then looks at the scoring rule, and they get to decide, am I going to run this costly survey, or am I just going to say something and not run the survey? Okay. And we use kappa for the cost of the signal. And then the agent will report a prediction to the principal. So you can think of this prediction as, it will be their Bayesian posterior belief. So if they gathered the information, that's a posterior update on the signal that they observed. And so it's the best possible prediction they can make about, for example, the distribution over good and bad outcomes. Okay. If they didn't gather information, they'll just be reporting the prior here. We're going to assume, it's without loss to assume this is a proper scoring rule, meaning that truthfulness is optimal. So in step 3, the agent is always truthful about what they currently believe. So if they didn't bother to acquire information, they'll still just say the prior. They're not going to guess. It would be worse to guess. And if they did acquire the information, they'll say their posterior. Okay, and then the principal, so they get that updated prediction, and then they later observe the outcome, and they pay with the proper scoring rule, S of P omega. Okay, so a way to think about this process with scoring rules, and this way will not be surprising to many experts at all, is as a sort of menu of contracts. Okay, so previously we offered one contract, but you can observe that for any fixed prediction the agent makes, this induces a contract, and you know Jason was talking about these as well. So that says, if outcome omega happens, I'll pay you some function of omega. So P picks out one contract from a big menu when the agent reports P. So with that observation, you can rephrase this, and you know it's not some brilliant insight, but it's an interesting way to think of it, I hope. As the principal offers a menu of contracts. So the scoring rule, again, looks like a menu that's sort of indexed by P. And then in stage 3, when the agent reports a prediction, well, equivalently, they pick one of the contracts and they sign that contract. So you gave them a bunch of options, and then later they pick one and they sign it. And now by revealed preference, you can tell from the contract they picked which signal they got and what their belief is, if you use a strictly proper scoring rule, for example. So this is an indirect way for the agent to run a marketing survey and then tell the principal what they found out in the survey, because their choice of contract will reveal to the principal the information that the principal wants to know. Okay, and then at the end, when the outcome is revealed, we pay the agent with the contract that they signed, that they chose to sign out of the menu, T of omega. Okay, so let me draw this on the same drawing, on the same axes, and try to mention the differences. So the agent has a prior belief about what's going to happen before they gather any information. So P might be the probability of a good outcome, in this drawing. If they acquire the signal and they observe that the signal's realization is S, they'll do a Bayesian update to PS. So they've gathered some information and they have more information about what's likely to happen, and they now believe PS. If they observe that the signal is D, they now believe PD. There's an important difference to the hidden action model. In hidden action model, the agent got to pick where on this line they wanted the world to live. They got to choose the reality. Is it really coming from PH if I take the H action? Or is the distribution really coming from PL if I take the L action? In this model, the agent doesn't get to pick, but they can observe. They can learn about where the world is. So it's an important distinction between the two. In this world, in this world, you can see that one contract is not going to be enough to incentivize the agent to gather information. The reason for that is that in expectation over the signal, sometimes the signal is S, sometimes it's D. And I've put on this drawing the points where the expected score will be if it's S and they report truthfully, and if it's D and they report truthfully. But on average, over those two things that could happen, their expected score is still the same as if they never acquired information and just reported the prior. That's because of linearity of this contract. So if I just offer one contract, and this is kind of obvious to scoring rule experts, but if I just offer one contract, there's no incentive to gather information here. You're not gaining any expected payment. Now, if I offer multiple contracts, the agent gets a choice. So we can see here that if they observe S, the signal's outcome is little s, then they have a higher expected utility, or expected payment if they pick the red contract and they sign that one. If they observe D, then they should pick the blue contract and sign that contract. So the choice of the contract reveals to the principal which signal the agent got. Okay. And if they just have the prior and they didn't acquire information, they should pick the blue contract as well. Okay. And so now you can also look at and start thinking about the increase in expected payment, and this is exactly the kind of thing that in Jason's talk he's trying to optimize for. The increase in expected payment if you do choose to acquire the information and you get to sometimes pick red, sometimes pick blue. And that's given by this gap in this drawing. And so, of course, the agent will look at that, and they'll look at the cost for acquiring the signal, and that's how they're going to decide whether they bother acquiring the signal or not. Okay. And again, this thing that I'm drawing is not optimal. It's just one example of something you could do. Okay, any questions there? Yes, please. Yes, good. So one thing that seems a little silly about the blue contract is I pay less for a good outcome than I do for a bad outcome. And that's especially silly in hidden action because it seems like it encourages the agent to try to pick points that are far to the left here because they'll get high expected payment. Whereas in information acquisition, it doesn't matter. So yes, depending on your setting, you might not want to do this, and you might want all of your contracts to be sloping up. However, I mentioned at the beginning, we're not actually explicitly modeling the principal's utility. And so we're even thinking of capturing a setting where the principal doesn't necessarily, maybe there are two possible outcomes, but the principal doesn't necessarily love this one and hate this one or vice versa. They're just kind of interested in some plan that they want the agent to take. And so in that case, you wouldn't necessarily have this phenomenon where you want to pay more for good outcomes and less for bad ones. Thank you. Okay, I think I still have some time left, and so I'd like to tell you what our model is in this paper. So contracts with information acquisition, the way we frame it is the principal offers a menu of contracts. The agent at the next stage gets to choose whether or not they go out and acquire information, like run the survey. If they do, they have to incur a cost kappa. Then the agent gets to pick a contract from the menu and sign it. Then the agent picks what action they want to take. For example, what kind of marketing technique they want to use, based on the signal if they acquired it, or just based on their prior knowledge if they didn't. And those actions have heterogeneous costs. And then nature draws the outcome, and the agent is paid T of the outcome, the contract that they signed. It's important that the outcome is drawn from a distribution that depends both on this hidden information and on the action that the agent took. Okay. And so, yeah, the agent might want to acquire the information so that they have a better sense of how their actions will impact their payments. Okay, and as I mentioned, we want to solve this minimum payment problem. So given a plan, try to design a contract menu so that the agent follows the plan. What do I mean by a plan here? So a plan in general is a contingent policy that says, if the signal, for example, is this, then the agent should do this action. But if the signal is that, then I want the agent to do that action. And if the signal is the other thing, and so on. So in general, a plan is a sort of contingent policy of what actions to take depending on what signal you see. And we want to incentivize that particular plan, or we want to learn that it's not possible to incentivize the plan, which could also happen. So the optimization problem looks very similar to Itai's at a high level. Minimize expected payment, subject to limited liability. Incentive compatibility says the agent wants to follow the plan. That's the best thing for them to do. And individual rationality says they get at least utility 0 in expectation. Okay, any questions here? And then we get to go back to the drawing. Yes, please.
So you assume that the agent can only have one signal, one-time signal, and you incentivize to show data signal.
That's correct. So we assume that there's only one signal out there in the world, and the question is, do I acquire it or not? A binary decision. And yeah, and we actually only consider plans that involve acquiring the signal, and we want to incentivize that. So we're not trying to figure out how to incentivize the agent to ignore the signal and take an action anyway, although that's also actually interesting in some settings. Okay. Good, okay, so let's talk about an example and put it on the same drawing. So in my example, let's say that the marketing survey that we run to gather information could find out that people like polka dots, but it might find out that people like stripes. Those are the two signal realizations. And we might find out that, or the agent is allowed to either run, let's call it instead of high effort, like a high class marketing campaign, where we show all of our customers like going to the opera and like eating wine and cheese and stuff. Or we could have like a low class marketing campaign where we show people in our clothes like going to punk rock concerts or like going to the club or something. So we have to decide what style of campaign we want to run. Okay? And in this, just for my example here, and in this example, let's suppose we find out the signal is S, so customers like stripes. And suppose for whatever reason we know the distribution that if we run that high-class campaign, the people who like stripes also really love going to the opera. And so there's a very high probability of a good outcome if we run that campaign when we know that S is the signal. But if we try to run the low-class campaign, maybe it turns out that people who like stripes really don't like rock concerts, and so the probability of success is very low. Conversely, just suppose for our example, if we find out that people like polka dots, we'll have a pretty good chance of success if we run this low-class campaign with going to the bar and going to the club, but we'll have a very low chance of success if people like polka dots and we try to show them drinking wine and eating cheese. If this were the way the world worked for whatever weird reason, a very reasonable plan that you might want to implement, is if people like stripes, then run the high-class campaign, and if you find out that people like dots, run the low-class campaign, which would try to get these two posteriors depending on whether you find out S or find out D. Of course, now you have to worry that any set of contracts you design might incentivize the agent to pick other posterior distributions here. And you also have to worry that the agent might be better off by not running the survey at all if it's very costly, and just taking an action, like just run the high-class marketing campaign and hope that it works, or run the low-class marketing campaign and hope that that works. The probability of the good outcome in this example for those is given just by the laws of probability. So if you run the high-class campaign, there's some chance that people like stripes and some chance that people like dots. So PH here is a convex combination of PHS and PHD. And similarly, PL is the same convex combination of PLS and PLD. Although maybe I didn't draw that exactly proportional. Okay, so these pH and PLs can't be anywhere. So these are the parameters that the principal gets as input to the problem, where all these posteriors are, as well as the costs of the different actions and the cost of acquiring a signal. And then the principal wants to solve the minimum payment problem. I want to make the pink circled things happen as cheaply as possible. Okay, and you can start thinking about, well, if I offer some menu of contracts, is that really going to work, or do I need to offer a different menu, or what should I do? Okay. Okay, we're done with part one. Questions about the model, please? Both the principal and the agent know all of these parameters, the distributions and the costs of actions and cost of signal. All right. Okay, so what I have to say here is I'm hoping it will feel very obvious, even if you're not that familiar with scoring rules before today. But we thought it's cool. So we make an observation that without loss of generality, you can view this menu of contracts as a proper scoring rule. And you can view the agent's selection of a contract to sign as reporting their belief about what's going to happen, their posterior belief. Okay. So I'll give you the picture in a second that will make this feel obvious if it doesn't already, which it might. But it's kind of a funny way to phrase this hidden action, hidden information problem, because the idea is the principal's sitting up in their office and they have no idea what's going on down there, and they just care about the outcome. But this is sort of saying, actually, you kind of have to elicit the information from the agent about everything that's going on down there. You have to use a scoring rule and get the agent to report to you everything they know. That won't quite be true because it's not going to be strictly proper. It might only be weekly, but I think it's just an interesting way to think about it. And here's another way to put it. You give the agent a proper scoring rule, which is just a score for how well they predict the future. And you design that scoring rule very carefully so that the agent thinks, how do I best predict the future? Well, I need to go gather some information about the future, and then I need to change the future by taking certain actions just to make my prediction very accurate. Okay, and you design the rewards for accuracy such that all these things they do to become accurate make the thing you want to happen. So I really like that, even though it's technically straightforward. Another way to state this, and this will be clear from the picture, another way to say it is you're designing a convex function G, and your menu just comes from tangents to the convex function. And Jason showed us this once, and then I'll show it to us again. And the convex function is sort of the pointwise maximum of these expected scores. That sounds jargony, but let me just show it. So here's the proof, and it's very similar to like the proper scoring rule characterization proof, which I've kind of just stated, so I won't state. You have any menu, which is just a whole bunch of these linear functions. Some of them might be redundant. What do I mean by that? Well, an agent would never choose these red contracts, right? Because for any belief they have, these contracts do not maximize expected score. Okay, so we could drop those without loss of generality, and we're left with only contracts that sort of could be optimal at some point. These trace out a convex function, which I've drawn in pink, and that's the theorem. These contracts trace out a convex function. Another way to phrase it is you could search for any convex function and then take the tangents, and that would give you a menu that, and you want to optimize over that space. Okay, so I'll try to say briefly some things about what we do, and hopefully have more time for questions. Any questions right now, though? Okay, so we spend most of our technical effort on just this special case of information acquisition, as we call it. So a very similar problem to the one that Jason talked about in the first talk of the day, trying to incentivize someone to gather information and report to you what they believe. This is simpler because we're interested in eliciting the full distribution over outcomes, whereas they were looking at the mean, and that's kind of a more complicated, harder problem. We also only have a limited liability constraint, so we have to pay at least 0, but we don't have any upper bound on the payments, which also makes our problem a bit easier. So this is what that special case looks like. It's the same exact setting, except in step 4, there's no actions to take. Okay, so you can think of this as the information acquisition problem. And the kind of general thing that had already been found out is that this V-shape type solution is optimal a lot of the time, or approximately optimal, and we're going to get the same, we're going to find the same thing. So the nice thing about this setting is it's simple enough to admit a closed form solution. So the convex function G star, this optimal solution, we first define a convex function H, and then we scale it to get G star. And G star is a V, a multi-dimensional V shape, which matches what you'd expect from reading prior work. And yeah, this H is kind of nice. It's sort of just a maximum over a relatively small number of contracts. So this is kind of what that looks like. You define the H, and then you scale it up. I should say in one dimension, like with binary outcome, good, bad, this is not as interesting, but I think the technical part is kind of interesting and exciting for me that this extends to multidimensional. So there could be many possible outcomes that the principal observing, and many possible signal realizations, like not just S and D, but many things you might learn, and all of this will still work. It's general. Okay. Let me skim forward quickly. As expected, didn't have time for the proof idea. I was hoping to say something quickly about the special case that's the hidden action model. So if there's no signal, no information, this model is just the classic moral hazard problem. We don't really have anything new to prove there beyond the many, many years of literature, but we have some drawings that I think are a nice way to think about it. Do I actually have time to say this, though? What? Yeah. Okay. Yeah, this is a good thing to spend 2 minutes on. So if you we're now just actions. So there are 3 actions in this drawing. You could take the low action, the medium action, or the high action. And they have different costs. And for some reason in this drawing, these are the costs. And you can interpolate those costs, and we would call that a cost curve, or the convexified cost curve. This is, yeah, okay, let me just say that. So this is an interesting object. So this is a function of a distribution, and it's telling you what is the expected cost to the agent to implement that distribution over outcomes. So you can even look at points in the middle here, and by randomizing over multiple actions, the agent can implement this expected cost for this distribution over outcomes, for example. The point is, this curve tells you feasibility. So if you have something that is above the convex envelope, that action is never going to be feasible. This is very well known, but people don't usually draw it this way. And furthermore, all the things that do incentivize an action are subtangents of this convex cost curve at the point, which again, I think experts would know, but they just don't like to phrase it this way. I think it's a cool way to picture it. So this is a characterization of all the things that incentivize the hidden action, except that you can also shift them up and down. Yeah, a way to see that is if I use this blue curve, the expected cost for taking the low action is higher than the expected payoff, so you would never do that. But you can take the medium action. So convex analysis kind of tells you what things look like. And so you can use this to solve the problem. But to find that subtangent, you still have to solve a linear program, so we didn't actually give a faster algorithm or anything. It's just a way to picture what's already being done. Okay, I should skim really fast. Main result, there's a polynomial time algorithm for solving our original problem, the general problem, because we can solve it with a linear program. So we can find a convex function that has a few pieces. So it's piecewise linear with not too many pieces. And finding the correct convex function there is just a linear program. And so that gives us an algorithm for the minimum payment problem. And we can spend some time in the paper trying to minimize the size of this LP, but that's the key point. I think the biggest open problem is, so in the standard hidden action problem, once you solve the minimum payments problem for a given action, you do that for all the actions, and that tells you what the principal should do to optimize the principal's own utility. In this problem, there's exponentially many plans that the agent could take, which is a map from signal realization to action. For any given plan, we can efficiently find the minimum payment to implement that plan. But the next question, I think, is, can you efficiently find the plan that the principal actually wants the agent to implement? So what is the best plan for the principal? Okay, thank you very much. That's all.
Great, thank you. We have some time for questions.
So I guess this may be more of a comment, but I think for your last point, we know that it's NP hard to do this, even in the case where like signals cost nothing. I think that's like exactly this setting of contracts with types, because the way I understand it, a plan is basically like a mapping from like a type, or I guess a signal to an action. And
let's see. So you're saying in the information acquisition, the pure information acquisition problem, even without hidden actions, or do you mean with just one?
I mean your full setting, but setting kappa to 0. So like basically they get their signal for free, so you don't need to worry about exactly the opposite of that.
Okay,
yes.
great. Yeah, I see. So, right, and in that case, there's an NP hardness from. Maybe I'll ask you offline, like the reference.
Yeah, there's some paper. There's some paper by Castiglione et al. And yeah.
Okay. Yeah. I'm not too surprised to find that it's NP hard, but it'll be nice to get that reference. Yeah. And of course, we're computer scientists, so we want to do simple and approximately optimal anyway, and that further motivates that style of approach to this problem. Mm-hmm. Yeah. Thank you for the comment. Anything else there? All right.
Other questions or comments? Okay. If not, let's thank Bo and all the speakers again. So that's a wrap for day 2. We're now going to break for lunch. See you all back here 9 a.m. tomorrow.